We're going to simplify, making the assumption that all the variables are any real number. Now, if they say they're any real number, we might be in trouble here because we have to be careful to slap absolute value bars on the answers of all of our even index roots. We have to make sure even index roots are equal to a non-negative number, so the absolute value bars assures us of that. So let's be on the lookout for that. Okay, part A, we have the square root of 45 m squared n. Well, we can factor the perfect square 9 and m squared out of that. And now we're going to move the perfect square portions of the factorization to the front under the radical sign. So that's 9 times m squared, and then the rest of the stuff, 5 times n, that stays in the back because that's not a perfect square. None of those are. Now we can bust apart multiplicatively the different square roots. The square root of the first perfect square, 9, times the square root of the second perfect square, n squared, times the square root of everything together that's left over that never gets busted out of jail. It stays under that radical forever because there's no perfect square factors in it. Okay, now let's evaluate the square root of 9. This is equal to 3. Now we don't have to put absolute value bars on 3 because we know the absolute value of 3 is 3. But the variable, we're not so sure. Let's see here. This is the absolute value of m, because we took the square root of m squared, times the square root of 5n. That's the part that never gets released from under the radical sign. So our final answer is 3 times the absolute value of m times the square root of 5 times n. Okay, the next radical is a fifth index, fifth root, so we don't have to worry about absolute value bars here. The fifth root of x to the 12. We're going to do it a similar way. We're going to factor out all the perfect squares and bring them to the front. So this is the fifth root of, let's see, we've got, I'm sorry, not perfect squares, but perfect fifth powers because the index is a 5. So in x to the 12, we have x to the fifth times x to the fifth, that makes 10, times x to the second. See, we added the exponents to make sure that they sum together to 12. That's what we had to make sure. We didn't give you more than what they gave us to start with, x to the 12. Okay, now we can bust apart multiplicatively each of these fifth roots. Fifth root of x to the fifth times fifth root of x to the fifth times fifth root of x to the second. Now the fifth root and the fifth power cancel because they're inverse operations, and it leaves us a factor of x times a factor of x times a factor of the fifth root of x squared. Okay, I did not put absolute value bars on it. I just want to make a big deal about that. Hey, no absolute values on our x's. Why is that? Because this was an odd index root, so we didn't have to do it. Doesn't matter whether the odd index root answers are positive or negative. They are what they are. Okay, so this x times x, I'm going to rewrite that in exponential form. It's x squared times the radical fifth root of x to the second power. Okay, and then finally we go to part C, where we're going to consider the square root of 243 times a times b to the fifth power. Now here we have an even index root. It's a square root, so our answer, we've got to be careful that we don't have any non-negative answer. So we might have to use absolute value bars here. Let's be careful. First, we're going to factor any perfect squares out of what's under the radical sign, the radicand. You know, 243 is 81 times 3, and 81 is a perfect square. And then b to the fifth can be written as b to the second times b to the second times b. We'll put that b in the back, and don't forget the a. So I moved the b in the back because I have this tendency to put things in alphabetical order. Something I should probably get over, but anyway. So here we're going to move next all the perfect squares to the front under the radical sign. 81 times b squared times the rest, 3ab. Those are the lifers. They never come out. Now bust it apart multiplicatively. Square root of 81, square root of b squared, and the square root of the rest of the stuff, 3ab. Now evaluate the square root of perfect squares. Square root of 81 is 9 times the square root of b. Well, it's just the square root of b squared is just b because the square and the square root cancel. So we get two factors of b times the square root of 3ab. And writing our answer in exponential form, we get 9b squared times the square root of 3 times a times b.